Okay, so in this video, we are going to talk about one of the very famous an algorithm, so machine learning models called a decision tree. So, and this is one of the most popular one, and we're going to talk about so a little bit theory underneath of that, um, and some idea when shall we use it and when we shouldn't use that. So basically, decision tree is used, I mean, almost every day's decisions. So basically, this is the white box, um, um, like machine learning models. So one of the things that we use all the time is called flow diagram or flow chart. So like flow diagram or flow chart is kind of visual representation of this kind of decision tree. Um, and this is and the whole idea of this decision tree is defined by the hierarchy of the rules. For example, which one should be true or false, and then goes to the left branch or the right branches. And you think about this ways: if we want to determine whether this animal is mammal or not, so this is a quick flow chart that we can do. So first things that we check is whether and what is the body temperature. If the body temperature is cold, that will be non-mammal. If the body temperature is warm, we will check whether it give birth or not. It give the birth, with mammal. If not giving a birth, that will be non-mammals. So each row and rule forms some like thing called like internal node, and this internal node will test the value of some properties. And for example, right here is like and the body temperature or whether it give birth or not. So we have a root. So this is basically the root, and these are the leaves of the node, which is the decision node at the end. So decision tree learning is that basically we training this data to construct or fit a decision tree models. Basically, we find out and these like rules and the leaves right here. So at the end, we are going to using this trained decision trees to predict for this new input. So and also and one of the very important and advantage of the decision tree is very easy to interpret, and it's a white box models. So you can have a good idea how this model make made these decisions explicitly. But of course, there will be other and disadvantages, and we're going to talk about a little bit later. So this is actually give you some more like precise idea about this and advantage means. So other models we have mentioned, for example, and probably you have heard about like in deep learning or neural network, and usually don't have these properties because they are more like treated as a black box models. That would be very hard to interpret how these input and data being transformed into output. So that's why, and usually, and this decision trees has this kind of way to make and everything very easy to interpret, and it's very similar to like human decision making process. You can easily and explain this whole process to your boss. So this is very popular during this business models, and this is being used a lot in the business analyst. And also there are a bunch of other and algorithms to actually to learn these decision trees. And for example, C4.5 is one of the and algorithms being used to learn and to train these decision trees. There are a lot of interesting and algorithms and to train the decision trees. But in this courses, we're not going to talk about this. So we talk about so the math and how we construct these decision trees explicitly in the machine learning courses. Okay, so by default, this decision tree classifier usually using the Gini impurity and measure. So and you need to ask and answer like what is the Gini impurity in these cases, and this is also a very frequent asked questions for the interviews. But you can also select entropy instead of and the Gini impurity as well. So this is basically some like hyperparameter that you can choose to either using Gini impurity or entropy. So this is basically and being defined in this function called decision tree classifier from scikit-learn. But the question is, which one shall we use for the measure, and whether it's Gini impurity or entropy? The actual things, I don't think there's any reason here. But there's slightly different things. It's like Gini impurity is slightly faster to compute. So that's why it's a good default. But however, there is a slight differences if they actually differ. And the Gini impurity tend to isolate the most frequent classes in their own branches, while entropy tend to produce slightly more balanced tree. So this has slightly differences, but for the most of time, it will not make too much differences. Just because Gini impurity is slightly faster to compute, because it's basically a quadratic function here. But for the entropy, you actually have to take the logarithm, and usually take the logarithm is more expensive than take the quadratic of the numbers. So that's why impurity is faster here. So let's consider a very simple examples for the iris data that we have. So we're going to load this iris data. So this is a very typical a data set that we're going to use. So in this case, we're only going to use these two features. One is petal length and one is petal width. But technically, I think and that array and that iris and the data has 4 columns. One is sepal length, one is sepal width, one is a petal length and a petal width. So we have 4, and actually we have 4 features. But here we're only going to use and we're going to use just 2 features. I believe it's petal width and the petal length. And our target is we want to predict and what kind of flowers we are working with from 0, 1, 2. Okay. So for example, if we are going to train a decision tree, that would be very simple. So this is, and you probably already know that. So here what we're going to do is we're going to train and the decision tree classifier with the maximum depth equal to 2. So this will be your tree classifier. Then you're going to fit X and Y directly over here. So this actually fit, and then this class is being fitted right here. All right, so then so you can predict if I'm saying my petal length is being 1 and the petal width is being 2, it will be classified as the 0th class right here. And of course, this is my decision tree, and I enforce this tree to has the maximum depth of 2. We can actually plot this tree and it will look like this. So this is kind of like an export graph to visualize the trees right here. So you can see right here. Let me just do this tree things one more time, because I want to make sure they only have 2 layers. So what they do is by default using Gini impurities here. In total, we have 150 examples. Then the value here, we have 50, 50, 50. Each class has 50 values, so it's balanced. So then what we do is, and the left is true and the right is false, right? So if it is true so we will this like rule or the root of this decision tree is petal length, which is less equal than 2.45. If that rule is true, that in fact we can perfectly separate the class of Setosa, that we have 50 of that, which is class of 0 right here. So that means that's why if we apply 1 and 2, which that means my petal length is actually less than 2.45. So that's why it will automatically predict it will be class of 0, which corresponding to Setosa. However, if this this condition is false, so we will go to the second layer. So, and this is the node of my decision tree right here on the second layer, which to check this paddle width, if whether is the paddle width is less equal than 1.75. So, if it is 1.75, if it is true, it will go, fall into the left, which is a 49 of that will be a class of 1, and 5 of that will be class of 2. If it is 4, then the 45 of that will be class of 2, 1 will be class of 1. So you can see at each of the leaf, this is not pure. The pure, that means we only have a one class. In this case, we are going to take the majority rules. That means, if this and the rule is true, then we are going to classify this as being in a class of 1. If the if the this rule is false, we will class this as the and a class of 2 by taking the majority rule right here. Okay, so we can take this prediction right here. So if we take, and this is a simple plot to plot this and the decision boundary here, because here we only have a 2-dimension data here, so we can just and exhaust all possible and the value for these 2 dimensions to see and what classes they belong to. So if we make this decision, this is actually the map we are trying to do here. So you can see right here. So on the first way that we just make a separate on this petal length, and you can see on this petal length, and we separate from 0 versus class 0 and versus class 1 and 2 right here. But from this plot, we can tell for this 2D and a 2-dimensional feature, there's no way to separate class 1 and class 2, right? Because they all merge together. And we cannot find a straight line somehow to separate these 2 features perfectly. So as the result, we are going to draw a line for the petal width right here, and such that it can separate as much as possible. But you can see some of the green dots is being classified as blue, and however, I think one of the blue dot is being classified as green. So, and the way that we set, this threshold is due, and by using this Gini impurity here, this basically ensures, if we set these rules on both party, on both leaves, and the Gini impurity is minimized. All right, so this is what you are getting here. And of course, if we don't specify any maximum depth, you can always just do fit. In fact, you are getting this graph like this. So basically, we have layer 1, layer 2, layer 3, layer 4, layer 5. So basically, we have 5 layers. And you can see right here, we are trying to make things overcomplicated. And still, we're going to check whether the petal length is less equal than 2.45. If it is true, it will go to the class of 0. However, we need extra 4 layers to classify and to perfectly separate out the class of 1 and versus class of 2. And the many node in this cases, you see we only need to separate 1 or 2 and the numbers. These can be easily considered as the noises. So that's why, and you can see these and these things could be and easily not useful at all, and it could lead to some overfittings, because these rules are just trying to separate something that is noises. So that's why, and you can think about the more the more layers of my decision trees, and the whole model is gradually going to more and more overfittings. However, we know we don't want overfittings, So we need to think about a way to regularize this decision trees. Okay, so if we actually plot this out, it will look like this. So you can see, yeah, I mean, sort of things that and we get is we're trying to separate these things like perfectly. Wait, what I'm doing here? Oh, I need to run this. Okay. I need to run this one. Okay, so I mean, this is what you are getting here. So you will see right here, I mean, you can see this whole and the whole boundary is getting like really complicated. You can see like some like unnecessary like zag and a zigzag. I mean, it's like handlebar to and a stick out to just to accommodate these two and a data point right here. But you can think about these two data point could be just easily and the noises and the like much more natural things is to set is we're going to draw a line right here and draw another line right here. Then we're going to treat these 3 points just simply as a noises, right? Some like error thing, and for examples. So and that will be much more senses. And turns out, I mean, if we choose our decision trees like this way, and this will be much more robust than like doing something like that. So and this is very important. So you can see, I mean, if we do and using the decision trees without without like having any regularizations, and that means that decision trees could be and it could have very large layers, and as the result, it's likely to have some overfittings. So that means, I mean, if we want to like avoid overfittings, we need to restrict our decision trees freedoms during the trainings. There are a bunch of hyperparameters that depends on the algorithm that we use. There are 2 of this that we're going to talk about today, and I thought, and sorry, like 3 of that, and we're going to talk about today. And of course, the first one is maximum depth. So like how many layers that we needed for and to separate these data. So maximum depth is one of the very important features for and to regularize decision trees. For example, we can say the maximum depth of decision trees that we have is 3. So and that means that will and that we only have like and at most like 3 layers. And there are and also other like options to regularize, for example, the maximum features. So this is the maximum number of features for which to search the best partitions. I mean, this is kind of necessary if we have a really large number of features, because it will be really expensive to search to partition all these features. So this is very important if we have like 1,000 features. And also there will be like minimum sample leaf. I mean, so we need to enforce the minimum number samples to be in a leaf. So and this actually prevent creating a trees where any leaf can only have a few members. For example, right here, and for example, this leaf we only have 2 members, and for this one we only have 1 members, and for this one we only have a member and 1 member. If we enforce the minimum sample leaf to have at least 4 samples, then all these of them and should not exist. So basically everything right here we should being pruned out. And because if we keep having this, that will violate the minimum sample and minimum number of samples to form and leaf. Also, and right here we can, and we're going to show this idea on the moon data right here. So this is basically the moon and making a moon data. So this moon data will look like this right here. So you can see, and this actually looks like a 2 moon and like tangle to each other. So this is and a class of red, and this is class of blue. And obviously this is very hard problems. And for the reason that, I mean, there's no like straight line to separate these two data sets. I mean, even with this, we only have two features, which is x1 and x2 right here. However, I mean, this is quite complicated and problems, obviously. Okay, so we're gonna create this moon data set right here. So we're gonna create a 150 and a 150 examples, and the noise is 0.2, and we're going to train two and a classifier, and like the entry classifier. One is without any regularizations. The other one is we have regularization that the minimum sample leaf have and has to at least two. Right, so these are the two different antecedent trees. Okay, if we actually using these functions right here, we to plot it out, we find out this is what we are having here. So this is, left one is the, the decision boundaries and without any kind of restrictions. So you can see we still have some error right here, but you can see right here we have created, decision trees that we have some like unnecessarily and a zigzag, for example, right here and right here and right here, to ensure and everything right here is to be and we predict everything and right here to be and red, and everything right here and right here will be blue. But you see, this is like doesn't look very nice because it might have some like unnecessarily zigzag. So we're going to imposing the regularization to imposing the minimum sample leaf has to be at least two. So like with that cases, we are getting this decision boundaries look like this. So this looks much, much better. And there's no such kind of unnecessarily zigzag. And most of them are just like and big straight lines. So and with that, it's seems like much more reasonable here. But of course, this doesn't look too much like. Let's try the different random state, and because like with a different random state, and this decision trees will look different. All right, it looks like this. It doesn't look right here, so let me try a different one. Let's do 12 to see whether they can using different version of that. Some of this, yeah. Maybe we can do and it's slightly different. Okay. Okay, that looks good. In fact, I think this is look better here. You can see it actually create and it zigzags. I think 2 is still too much. Let's try 5 here. Okay, so I think that's good right here. All right, so as you can see right here, if we don't have any like restrictions, so and you can change all these random state here, and to ensure this is and have a different like and random seeds. In fact, these decision tree classifier is very highly susceptible to those like and a random state. So basically, if you change your random state a little bit, these decision trees could be dramatically different. So this is one of the reasons these decision trees could overfit, because if you change your data, just like and slightly perturb your data, if you don't imposing any kind of regularization, that kind of decision trees could be dramatically different. So this is one thing that you have to keep in mind. And this is one of the big like and disadvantage to use any decision trees. Okay, if we do something like that, if we don't have any restrictions, you can see there, and we have like unnecessarily and a zigzag to ensure we include those like red points right here. And we have completely unnecessary like handlebar right here to include these two like red points. However, if we enforce this minimum sample leaf to be 5, then we only have these zigzags, which both of that is pretty like big lines. And they are quite reasonable, I would say, although we have higher training error. We have some point right here, some point right here being classified as red. But these are the errors that is okay, and we can tolerate this amount of error here. So that's actually verify that with with the different like random samples here. So let's see whether we can get an additional maybe 2,000 points. And let's see. So on the first one that we got is we getting like 95% of accuracy here. On the second one that we got is 94% of accuracy. So in this specific cases, we found out actually, and without any restrictions, our scores, it turns out better. And with this minimum sample leaves, so equal to 5, then we only get 94% of accuracies. So you can see, like if we have the first trees that we get, like and the maximum depth is 7. On the second one, the maximum depth is 6. So this is only like 1 and 1 layer lower. And we can try something a little bit more, see whether it makes sense. So let's try this to be 7. Right, let's try this to be 7. See whether we are getting it right. Okay, looks same. Maybe try something slightly different here. Okay, still the same. All right, maybe we can try a little bit bigger. Let's try 500. This is looking quite good. This is kind of like unnecessary zigzag right here. And then let's see whether it, has a different result if we have 2,000. Right, that's a good example that if we using 1,000 data setting, like 500 like any data set again, still we assume my minimum sample leaf is has to be, and let's say it's 10 right here. See whether it gives you a better result. Okay, so you can see we have some like unnecessarily zigzag right here. It's getting and make this like and the decision boundaries overcomplicated. With that, we create a new testing data set of 2,000 data set. Then the first, and without any regularization, the score's getting like 95%. With this regularization, actually we're getting 96% of accuracies, which is slightly better. And you can see if for the previous one, we have the maximum depth to be 11. If we, and the width, regularization, the maximum depth is only 6. So this is significantly smaller. So this is just give you some idea that and regularization is actually absolutely necessary here. And of course, decision tree can work on the regression problem here. And so decision tree is very powerful. It can work on the classification. It can also work on the decision trees. So and regressions. So for the regression, they usually use some algorithm called CART. CART. And we usually talk about this in the machine learning courses. So basically, and the criteria for this and regression is changed. I mean, it's no longer being the and accuracy here. It's actually the variances that we are being interested. So basically, we are trying to minimize and the variance and of our predictions right here. So this L is the number of the samples in the leaf. Yi is actually the value of the target variables. So basically, if we like minimizing the variances, and we want to look at features actually to divide this training set in such way the value of target in each leaf will be roughly equal. We're going to talk about this right here. So we're going to create some data. So this is just one single input feature. So it's super simple. I mean, this is x squared plus some and random noises here. So we're enforcing them like maximum depth equal to 2 right here. We do this fit. We do this plot. So this is basically the the plot that we have. So that means everything that is less equal than minus 0.3, the value will be 1.72. And then we are going to set if this is further smaller than minus 0.4, the value will be 0.213 and so on. Right? So this at each intervals, they are going to using a constant to approximate that. So we can plot this out as well, and we can do this. Wait, it's right here. So, and this is my decision trees for maximum depth is equal to 2 right here. So you can see we are splitting, and this is my data here, and which is roughly quadratic. So what we do is we are trying to split my data into 2 layers. The first layer is going to split right here, left and right. And on the second layer, it's going to split right here and right here. And during each interval right here, we are trying to using a constant to approximate the data point in these intervals, right? So you can see this is a really rough approximation, but that's how the decision tree is making the prediction right here. So they are trying to using one constant values to make predictions within these intervals. And this is, we enforce this to be and a maximum depth equal to 2. However, we can make this to maximum depth equal to 3. So I mean, as a result, we are getting more and more and a different threshold here. And this is and the threshold for the maximum depth equal to 2. This is the threshold for the maximum depth equal to 3. So I mean, for this case, we are having 1, 2, 3, 4, 5, 6, 7 different threshold. On the top for that we have 3 threshold that we're getting. For this and for this threshold right here, it looks pretty large. We have 1, 2, 3, 3 layers. And if we plot this out, we are getting maximum depth of the trees to be 3, and to be precisely, we're still trying to split for and right here, and these two are still the split for the second layer. However, we have additional split here, that each interval is going to be approximated by the constant. Okay. But you see, this is still a very rough approximations. But in general, if we try to using, decision trees to approximate random quadratic functions, it doesn't usually give a very good job right here. All right, so so we can do something different as well. You can say, if we don't apply any restrictions, in fact, that's kind of the and the decision boundaries, the functions that we're trying to approximate. Because if we don't pose any kind of restrictions, they will create the decision trees trying to connect every point for these decision trees. On the other hand, if we enforce that the minimum sample leaf equal to 10, so that means at each leaf, it has to at least have a 10 points. So we are getting some like leaves that is quite reasonable. I'm still zigzag, but I mean, with that, it looks much more reasonable than the one without any kind of restriction. And this one is more reasonable than the one we only have a maximum depth equal to 2 and a maximum depth equal to 3. Because this is super rough, it's like way too rough. And the same here as well. So we will consider on those two regions to be underfittings. And because it doesn't like fits very well right here. But of course, we can use cross validations to find out what is the best maximum depth in these cases. But I mean, if we don't, I'm imposing any kind of restriction here, this is clearly overfittings because we're trying to create the decision trees that to ensure it passing through every point, which obviously it's absolutely not necessary. So we can try to see how many layers that we actually get in these cases. Let's see how to check the layers. So that's the command. Instead of it's reg, okay, reg. So the maximum that we get is 15, and which is quite big. If we switch this into regular 2, we are getting 7s. So you can see right here, so this is significantly smaller and maximum depth compared to and without any regularizations, right? So, and like with the 7 depth and the 7 maximum depth, it actually fits the data very well, and much better than and with only like 3 layers, and also and much more reasonable than 15 like layers. However, and there are other issues in the decision trees here. So one of the issues is decision trees only choosing these kind of orthogonal decision boundaries. So as you can see here, all the split is always perpendicular to a certain axis. It's always like this. It's like always like, I mean, if we check this like boundary condition, it's always perpendicular to certain axes. Either x1 or x2. So this is some like rules coming from what we have, and which is very sensitive to the data of orientations. And for example, the data of like this, if it is linearly separable, and like that, all we need to do is just like draw a straight line to separate these and red points and the blue points. However, if we rotated this data by 45 degrees, then we still apply the decision trees. Previously, right here, we only have 1 layers. But with that, actually, we are getting more layers because we have some like and zigzags right here. That just indicates the only thing that we do is rotate by 45 degrees, and that we actually need to using more layers of decision trees to fully separate these two data, right? So that means this whole thing is very, very sensitive to the axis orientations. Although like both decision trees fits the training set perfectly, but the problem is the model on the right and may not be generalized very well because it start to create some unnecessary zigzags right here, which makes whole things more complicated. One way to solve this problem is we can apply the PCA and transformation first, and after that, then we can apply this decision trees classifier. So this is a very common approaches for this kind of decision tree classifier first. And instead of we do any kind of and like standardizations or data transformations, we instead are using the PCAs and such that and everything and it will be scaled and rotated into more like it's more like perpendicular to the axis. So this is very important because if we don't do that, those kind of decision trees may very likely to overfit. So this is also a very common ask questions during data science interviews that you need to make sure you understand this. What is the limitation of the and the decision trees? Why we have to apply PCA first before we using the decision tree classifiers? So this is the reason. Okay, so if we actually do the PC and create this pipeline, we create this standard scalar, and then we create and apply this PCA here, then we do this and whole transformations. Actually, what we are getting is something like that. We're actually trying to separate on this like in a depth of 0. Then we separate again right here for and a Z1 here. So you can see this is basically very similar to what we have, but instead, and all these three features are, are rotated and transformed in a way that they are most likely to be separated by the axis that is perpendicular to certain axes. So this is the situation or the benefit of using the PCAs right here. So that's why I mean, this is very important. I mean, it's like, and it's always a good idea to apply the PCAs before you do any kind of the decision tree and a classifier. Even the PCA doesn't and reduce dimensions from high dimension to low dimensions, but and this is already rotated data a little bit, and to ensure this kind of the vertical line of or horizontal lines can separate and these classes as much as possible. Okay, another limitation here, and we already mentioned this, in fact, that that decision trees has very high variances. And that means if we make a tiny changes or small changes of the data set, it could like produce a very different decision trees. So and let me show you this like and the training and the same model with the training and the same data, but it might produce a very different model every time. I mean, the reason is because I mean the algorithm of training and the decision tree is stochastic, and as I said, it depends on what kind of random state that we use, and to show that, and we can change the that random state in a different number. Here we're choosing 40, and I want to remind you right here, I think we choose this to be 42, right? But everything else is being the same. And if we choose the random state to be 42, it's split right here. However, if we choose this into 40, oh, that's X. Okay, so I want to remind you this, and this X or Y is the one on the top right here. Right here. So that's the XY right here. For the XY right here with the two layers that we got, it actually using something like that. So let me just trying to reproduce this result. This is the plot of the pre. This look like that. Okay, so we got like, and the plot looks like this. We have and the pedaling that pedal with like this. Okay, so with that, if we don't if we don't imposing, so if we, and still choosing the maximum depth equal to 2, but however, we changed it, I mean, this random state right here, and that's the only thing that we changed. We are using the same data. It actually separate on a different point right here. And I want to remind you, previously we separate on here, then we separate right here, right? But here, if we change this random state to 40s, the first layer is being split right here. And of course, we still have a perfect separations from class of 0 and the class 1 and 2s, right? So, and instead of we do split right here, this actually choose the petal width as the first split right here. In the meantime, and the second split will still be the same right here to split the class of 1 and a class of 2. So you can see right here. So this gives you some idea. Even we using different random seeds, it will give you a different and decision trees. So and it is, it's highly and susceptible to those data changes and highly susceptible to those random seed changes. So that's why the decision trees have very high variances. That indicate if you don't regularize it well, it's very, very likely to have the situation of the overfittings. We don't really want our model to be overfitted, so that's why we need to using the cross validations to find out the best hyperparameters for our models. This is absolutely necessary for the model of decision trees. If we don't work, if we don't and using this approach, and this decision trees is basically still a garbage. We cannot use that. All right, so there are other approaches to and mitigate the effect of overfitting. One of the ways is we are going to take advantage of something called ensemble method. So that's something we're going to talk about in the next videos. All right, so that's all for this video.